So from high school physics, we know that if the dot product of two vectors is equal to 0, then the two vectors are perpendicular to each other or orthogonal to each other. Let us now define a similar notion of orthogonality for a general inner product space. So let V be an inner product space over R. So again, over F, sorry. Our vector space could be a vector space over R or a vector space over C. Doesn't matter. The definition holds. Then we say that the vectors V comma W in capital V are orthogonal to each other, are orthogonal and denoted V orthogonal W if the inner product of V and W is 0. So for example, if you look at 1 0 and 0 1, they are orthogonal with respect to the standard inner product. In fact, they are orthogonal even with respect to the non-standard inner product which we had defined earlier, which was 2 times the standard inner product. Even with respect to that, these are orthogonal vectors. Let's take an example to depict that the orthogonality is a property which is very much dependent on what inner product we consider. So let's consider P of R. So consider x minus 1 by 2 and 1 in P of R. And let's look at what will be the inner product of these two. Then the inner product, so let's look at, we had defined two different inner products. Let's look at the inner product of these two vectors with respect to both these inner products. So the first one was x minus half and 1 was what? 0 to 1, x minus 1 by 2 times 1 bar dx. And this just was equal to integral 0 to 1, or let me just write it down, x square by 2 evaluated from 0 to 1 minus x by 2 evaluated from 0 to 1. Actually it is minus x by 2, which is evaluated from 0 to 1, which is equal to 0. So yes, x minus 1 by 2 and 1 are orthogonal with respect to this inner product. Let's see if it is orthogonal with respect to the other one, x minus half comma 1. Let's put a prime here to denote that it's a different inner product. This is just in the integral minus 1 to 1 of x minus 1 by 2 dx, which is equal to x square by 2 minus x by 2, which is from minus 1 to 1, which is equal to 1 by 2 plus 1 by 2 minus minus 1 by 2 minus 1 by 2 plus 1 by 2, which is equal to minus 1, which is not 0. So these two vectors or these two polynomials are not orthogonal with respect to the second inner product. So the two vectors being orthogonal very much depends on which inner product we are considering. Let's look at one more example to show the other way. Let's consider two vectors or two polynomials which are orthogonal with respect to the second inner product, but which is not with respect to the first one. So consider just the polynomial x and 1. And what is the inner product of x with 1? This is just, let's put a prime here to see what happens for this. This is minus 1 to 1 x dx, which is equal to x square by 2 evaluated from minus 1 to 1. That's a definite integral which is just going to be 0. So yes, x and 1 are polynomials which are orthogonal to each other with respect to the second inner product. However, what is the inner product of x and 1 with respect to the first one? This is 0 to 1 x dx, which is just, let me just write it down, it's going to be half. So this is not equal to 0, so they are not orthogonal with respect to the first inner product. So orthogonality is a relation which very heavily depends on which inner product we are considering. So being orthogonal is in some sense the other opposite extreme of being parallel. So if you notice Cauchy-Schwarz, we had noticed that in the Cauchy-Schwarz inequality, if a vector w is a scalar multiple of a vector v, then the inner product of v and w is the absolute value of the inner product is equal to the length of the product of the length of the vectors v and w. That is one extreme, and the other extreme is when it is 0, and that's precisely when v and w are orthogonal to each other. So the extremes are when it is parallel and when it is orthogonal to each other. So orthogonality captures the other opposite extreme. Yeah, orthogonality is a symmetric property. So if v and w are orthogonal, so let me just note that orthogonality is symmetric. If v is orthogonal to w, w is orthogonal to v. Orthogonality is a symmetric property. Okay, so the next proposition which we will prove tells us that orthogonality is a property which is preserved if you consider a linear combination of vectors. So let me write down and clarify what I just said. So let V be some inner product space over F. So let V be an inner product space over F. So it could be a real vector space, real inner product space, or a complex inner product space. This theorem holds for both the cases. So let V be an inner product space over F. Suppose V1 to Vn are vectors in V which are orthogonal to another vector, say small w, in capital V. Suppose each of these vectors v1, v2 up to vn are orthogonal to w. Then the proposition tells us that any linear combination of v1, v2 up to vn will also be orthogonal to w. Then any linear combination of v1 to vn is orthogonal to w, small w. Okay, let's give a proof of this proposition. So let's consider some linear combination of v1, v2 up to vn. So let a1 v1 plus up to an vn be a linear combination of v1 to vn. So here a1, a2 up to an are scalars. So if it is a complex vector space, a1, a2 up to an are some complex numbers. If it is a real vector space, a1, a2 up to an will be some real number. So what will be the inner product of, so we would like to show that the vector a1 v1 up to an vn is orthogonal to w. We would like to show that this is equal to 0. But by linearity, by an induction argument on linearity, I will just leave it as an exercise for you to check. that this is A1 times the inner product of V1 with W plus A2 times the inner product of V2 with W plus dot 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 AN times the inner product of Vn with W. But what do we know about VIs? Each of the VIs are orthogonal to W. Since VI are orthogonal to W, Vi comma W, the inner product of this is equal to 0, and hence A1 V1 plus AN Vn inner product with W will just turn out to be the 0 scalar. Hence, that's the definition, i.e. A1 V1 plus up to AN Vn is orthogonal to W. So in particular, if so we have proved the result. In particular, if we take some vector V which is orthogonal to W, and if you look at any vector in the subspace spanned by V, that will also be orthogonal to W because it's a linear combination of V, right? So in particular, let me just note that if V is orthogonal to W, so is C times V, where C is a scalar, and hence the entire subspace, any vector in the entire subspace will be orthogonal to W. So one of the first results that comes to our mind when we consider perpendicular vectors is the Pythagoras theorem. It's one of the oldest theorems which has been known to mathematicians. We will now prove that a version of Pythagoras theorem is true in an inner product space. So the celebrated Pythagoras theorem. So as you can see, all the famous classical theorems are getting generalized. So this is clearly the right notion to look at. So let V be an inner product space over F. So either a real inner product space or a complex inner product space. The Pythagoras theorem that we are going to state down holds. Then for orthogonal vectors V comma W in capital V, we have the length of V plus W square is equal to the length of V square plus the length of W square. So the sum of the two sides of a triangle, a right triangle, is equal to the square, sum of the square of these two sides of the triangle is equal to the square of the hypotenuse. Okay, let's give a proof of the celebrated theorem in the case of an inner product space. So what is the length of V plus W square? That is just the inner product of V plus W with itself. But our inner product is linear in both the first variable and conjugate linear in the second variable. And using that, this is just going to be equal to VV plus VW plus WV plus WW. But what do we know about V and W? We know that V and W are orthogonal vectors. So this inner product vanishes, this inner product vanishes, because orthogonality tells us that the inner product of V and W is equal to the inner product of W and V, which is equal to 0. What is this? This is nothing but the length of V square plus length of W square. So the inner product and the properties therein gives us a very compact and an elegant proof of the Pythagoras theorem. In fact, we can say a little more about a more general version of the Pythagoras theorem, in fact, can be proved. So let me just write that down. Let me call it generalized Pythagoras theorem. Pythagoras theorem. So if let V be an inner product space over F, and suppose V1, V2 up to Vn are vectors which are mutually orthogonal. So let V1 to Vn be mutually orthogonal vectors. So what does that mean? i.e. Vi is orthogonal to Vj for I not equal to j. Of course, no vector can be orthogonal to itself. So it's an exercise for you to check that no vector can be orthogonal to itself. So let me have a look at what was the symbol used for orthogonality. Yes, so it has been introduced. So yes, V is orthogonal to itself is introduced by this particular symbol. So Vi is orthogonal to Vj. So maybe after I write down the statement, I'll give you an exercise to check that no vector can be orthogonal. In fact, I'll just mention it. So then, what does the generalized Pythagoras theorem tell us? It tells us that if you look at the sum of these vectors, look at the square of its length, this is equal to square of V1, length of V1 square plus length of V2 square plus length of up to Vn square. So this is the generalized Pythagoras theorem. Okay, so how do we prove this particular theorem? We shall prove this theorem by induction. So let us prove this result by induction. Now, in the case when n is equal to 1, there is nothing to prove. So the case n is equal to 1 is clear, and n equal to 2 was just proved, and n equal to 2 was just proved above. So for n greater than 2, let's impose the induction argument. Assume the result to be proved up to n minus 1. Let's prove the result for the case when n comes out. Alright, so before we get into any of that, notice that V1 is orthogonal to Vi for I greater than 1. So for I equal to 2, 3 up to n. So let me write it like that. And by what we just proved a few minutes back, if you have a vector which is orthogonal to a collection of vectors, then it will be orthogonal to any linear combination. So in particular, hence by a previous proposition, let me use the symbol for orthogonality. V1 is orthogonal to V2 plus V3 plus up to Vn, because it's orthogonal to each of V2, V3 and so on. And that means now by Pythagoras theorem, not the generalized, we are proving the generalized one by the Pythagoras theorem for two orthogonal vectors. The length of V1 plus V2 plus up to Vn, the whole square. This is nothing but the length of V1 square plus the length of v2 plus up to vn square. But we have already proved the we have, by induction hypothesis, we have already assumed that the result is true for up to n minus 1. And if you consider v2, v3 up to vn, there are only n minus 1 mutually disjoint vectors. And by induction, this is equal to norm of v2 square, or the length of v2 square, plus up to the length of vn square by induction. So this is by Pythagoras theorem. I have written it above. Yes, by Pythagoras theorem we have this first statement, and by induction we have the second statement, and that's precisely what we had set out to prove. So we have a generalized Pythagoras theorem. As a corollary to if v1 to vn are mutually orthogonal, so I'll leave this as an exercise for you, then the length of a1 v1 plus an vn square, this is equal to mod a1 square length v1 square plus dot 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 mod an square length of vn square. So in the next week we shall try to get hold of a basis consisting of such orthogonal vectors.